something we have seen before, but let's go over it again, this idea of related rates of change. So sometimes to solve a problem we need more than one derivative to solve the problem. And it's basically using our idea of, we'll call it what you like, implicit differentiation, the chain rule, whatever, but it's all the same idea. Let's have a look at last year's HSC question. The volume of a sphere, yes, they give you everything because they assume we don't know these things. Oh, by the way, it's 4/3 pi r cubed if you couldn't remember. And it's increasing at a rate of 10 centimetres cubed per second. First part of the question is to just show that the rate of increase of the radius is that expression. So all right, we have to find dr to t. We've been given dv to t. So dv dr would be real handy because then we could link the two together via that other derivative, and we differentiate volume. It always amazes me, but every time I see it I look at it and go, oh, look at that. The rate of change of volume with respect to radius is the same as the surface area, because remember, surface area of the sphere is 4 pi r squared. Put it all together, we want to find dr to t, substitute in, and great. We've got what they asked us to show. 2018, so a few years before that. Ferris wheel, radius 20 metres, rotating around 1.5 radians per minute. Top of the carriage is measured, okay. So we talk, h is just the distance from the axis there, the dh to theta. We've got to find the expression for dh to theta. But we've got this nice triangle that has both theta and h. We should be able to get something there. h over 20 sine theta, we just differentiate that. Okay, that part was all right. At what speed is the top of the carriage rising when it's 15 metres high? That's probably higher, it should be, shouldn't it? Higher than the horizontal diameter of the Ferris wheel. So we want to find the rate at which it's rising. So h was measuring the height, that would be dh to t we're trying to find. So we just worked out dh to theta. It's 20 cos theta. To theta to t we've also been given, it was 3 on 2. I think they said 1.5, but I just made it a fraction. dh to t is what we want to find, and yes, we can use those two to link together to get an expression, 30 cos theta. But the information we know is h, not theta. So we're going to have to work that out. Draw myself up the triangle, a bit of Pythagoras. Okay. So I didn't bother finding theta. I thought, oh, let's just find cos theta straight away off the triangle, because I don't really need to know what theta is. And that turned out to be root 175 on 20. Sub that into our formula, we get 19.843. They said the one decimal place, so 19.8 metres per second. Distance A is inversely proportional to distance B, and the constant of proportionality looks like it's 9 for that one, so A is 9 on B. We've been given the rate of change of B. We want to find the rate of change of A when A is 12. Okay, dA to t is what we want to find. We've been given dB to t, again I've just made it a fraction. They've also told me that. To link it together, I'm going to want dA to b, aren't I? So, oh, that was a bit lazy. I didn't actually do the, well, I did the calculation but put it into the formula straight away. But anyway, that's what I've done, isn't it? I've gone dA to t is dA to b times dB to t, and we want when A is 12. Bit of calculation, we get minus 16 on 5. Decreasing rate 3.2. Okay.